Classical Physics Tutoring Prerequisite 2 and Vector Calculus. Now, the Prerequisite 1, we review the vector algebra. Now, this time we quickly review how to get the derivatives of the vectors. Now, I hope you learned that if f is function of x, y, z, multivariable calculus, you have three different kind of derivative you can take. Okay, and generally speaking, x can be time, y can be some other parameter, the density, z can be something else. Okay, but the vector calculus, in this case x, y, z's, are all coordinate value, and coordinate value can be the function of time. So you have a parameter derivative. So when you want to know the function change over time, so you take a derivative along the x, and you take a derivative on that x with respect to t. Okay, and I hope you learn this multi-variable class. Now, the vector can have I, j, k independent. So what happened is, actually vector is a multi-function, multi-variable. So vector A is axi plus ayj plus azk, and each ax, ay, az is multivariable function. So you have a three multi-function with multi-variable. Okay, so that's a vector. So it's just expansion of the single function multivariable. Now, this kind of function, there are several different ways to take a derivative. Depends on what you are looking for. Okay, so for example, contour diagram, you may have two small mountain, right? And if you are here, depend on which direction you go, the slope is different. So what happened is, if it is phi, the height, altitude is phi, then this gives the slope on the x coordinate side, and this gives a slope of y and z coordinate. Then net change, if you have dx, dy, dz. So dx, dy, dz depend on what the value you plug in, the net change. The derivative is, again, dz is a function of these three variables, depend on how you look at it. For example, here maybe zero slope, or here there is a slope. Okay, so the contour map is a kind of image you can have for the two-dimensional cases. And three-dimensional, it can be like a density change around, and you take one point, and depend on which direction you go, the density, the change of the density, slope of the density by coordinate x, y, z is a good example. Or you have a electric charge, and that creates a potential, spherical potential, and which direction you go, the electric field different. So that's all coming later in the physics. Okay, so when we learn calculus, we talk about how we can get the differentiations. So differentiations, it's pose some restriction on the function, right? For example, if you have this kind of function, then at this point differentiation becoming impossible. It has to be continuous, right? And cannot have a two value at this point. Then you have a two different differentiation. Okay, the 3D world, how do we set such a condition for differentiation? The easiest way the physics uses a flux. And what is flux? Flux is when you have a contour map, you put the water on the top, then water flow down from high to low. Okay, that's the flux. And originally it came from fluid dynamics, when liquid flow, what's happened. Say you have a source of liquid and second source, you have a sink. The water flow this way, and some of them may go round. Okay, but this is kind of a flow of the liquid, and there is a block, then the flow go right and left at this point. And here you cannot have this branch in the flux, means the velocity, there are two velocity at this point. That means differentiation will be not impossible but very difficult. So you can't have a branch in the flux. So we can deal with the physical phenomena. It doesn't have a branch. What the branch means, if the flow density is here, rho 1, branch out means rho 2, rho 3. That means the density is different from this point and this point, and that's we have to exclude. It's a different considerations. Okay, density is the same. That means in and out is always same, so it's a continuous line. Okay, so that's a kind of condition for differentiation. Now, the first differentiation is called gradient derivatives, and we define this kind of operator. Operator means it just apply to this function. Say you have a contour map or a potential, electric potential. The phi is here. Then you get this, and this pretty much give the slope of the contour map. Okay, that's a one of differentiation. And we also have another differentiation called divergent derivatives. So this time, this triangle, there's no dot here. We put the dot. This is important. Means we use like a inner product in the vector. Right? So the D is a vector, and inverse triangle is also vector. Let's see. Inverse triangle is also vector. So inner product is each vector element multiply dx over dx plus dy over y plus dz over dz. Okay, that's also possible. Okay, and if you use a polar coordinate, it's become like this by using conversion of the coordinate. Now this has another physical meaning. So we use this kind of derivative functions also, and this derivative function is for the vector d, and this derivative function is for the potential phi. Okay, and one more, a little complicated, the vector algebra, we went through this, the curl or rotation. Okay, is here it's a cross product, so it works like a cross product. So this ijk, the triangle, suddenly become this part, and the vector has element ex, ey, ez. Okay, so that derivative is defined in this fashion, and this has a very important application in the electromagnetic theory. Okay, and so polar coordinate, converting polar coordinate, we have this equation. The polar coordinate looks different for every derivative. This is the gradient derivative, this is divergent, and this is curl derivative. Okay, and if you repeat this, okay, then what's happened? This is that's what it means, right? So yeah, here, so this is a vector and dot inner product. So let's see precisely, this is same as, okay, so after you create a vector by gradient, you apply divergent derivative, so it's a second degree derivatives. Okay, so we write this inverse triangle square. Okay, and polar coordinate become a little complicated, but you can look up. So now here's the important things, gradient theorem. Okay, we will go through this in the actual physical theory, so you don't have to really worry too much about what this means, but it's just briefly understand where the gradient derivative used. Say you have a contour map and you have a point AB, and this flux defined E, and you take an integral along the E on this path. That's what this integral. Then actually you get the difference phi b and phi a. Okay, so that's the meaning of the gradient theorem. Divergent theorem means you take a divergent of the flux and take an integral. That means all the flux coming out from this area is going to be equal to all the flux going out from this enclosed circle, and this means integral within an enclosed boundary. Okay, so you take the E at the surface and integrate, collect all the E coming out from this boundary is equal to all the flux created within this area. That's a divergence theorem. Okay, and there is a green theorem. Green theorem is a little complicated, and I think you have to go through this in a textbook or some math book. I hope math class teach you. Basically, it's come down to, in the 3D case, this. The curl derivative, you take integral, that means certain area, you collect all the vector going through this area, okay? It's going to be equal to curl vector integral of this boundary. And it's just like a divergence. All the flux created here in this potato is equal to all the flux coming out. Make sense? In this case, all the vector within this boundary is equal to the vector integral along this boundary. So boundary determine the amount of vector inside, and this one is this boundary closed potato surface is going to determine the amount of flux created inside. Okay, so the curl is okay. Here's a boundary, and there is a vector inside the boundary, and they are related by this equation. Okay, so okay, don't worry too much about this because we're going to use it extensively in the college physics. So mathematical proof of Green theorem, maybe you can go through once you understand, then you don't need to go back during the physics tutoring. And the objective of having this Green theorem is to prove this physical relationship between the vector inside the boundary and boundary vector integral. Okay, so I think you are ready to start the college level physics now. Please move on to physics chapter 1, Newton's theorem. If you like this video, please subscribe.